I myself am actually right now located in Romania, more specifically in Transylvania, which sort of by default means that I probably do some kind of investigation on vampire activity. Do rest assured, this is only my side job, not my main job, because like Ashley mentioned earlier, I am a trainer for Opsgility. I'm also one of the passionate Azure MVPs, and I do have a lot of, at heart, I'm a software developer. So that by default also means that I like Service Fabric as an offering because it takes away everything I had to deal back in the on-premises days, back in the days of VMs and infrastructure as a service, and so on and so forth. Now, before we get right into our conversation and deep dive into it, let me tell you that I have no idea right now who you are. And I am so sorry for that. But here's the right context for you. I assume that you're either a software developer, an architect, or maybe an IT pro who sort of does have some part of responsibility in the entire DevOps cycle, in the entire story of DevOps, ALM, and so on and so forth. And Service Fabric is one of the things you're interested in. Have you ever heard of microservices? Great, because we're going to cover microservices. Even if you haven't heard of microservices before, that's also great, because part of our first conversation and the first topics today will cover what microservices are, what is a monolithic application, how do you break apart a monolithic application into microservices, why do we even call them microservices, and so on and so forth. We will also talk about, oops, what just happened? Do you still see my screen? Because I don't see my screen though. Okay, I'm good. Sorry for that. So, I will also talk about clusters and what Service Fabric clusters are. I will talk about application packages, Service Fabric services, and so on and so forth. There's a lot to talk about for the next hour or so. Also, if you ever have any questions, don't be shy. Go ahead, ask your questions in the IM window. We do have an awesome staff on standby, ready to take your questions and ask them ahead. And I myself, if I do get a chance to get the real glimpse on the questions window, I'll try to answer some of those myself. But I don't make any promises, because I'll be honest with you guys, I'm so passionate about this conversation, I sometimes just forget about doing anything else and stop talking. So sorry for that in advance. Now, here's the thing. When we talk about microservices, we have to ask ourselves, what are microservices in the first place? So the one way to put it is that microservices are programs, normally small, that serve a single function, right? They ideally do only one thing, and they do it very well, to be frankly honest. This is like the same principle as the letter S from the acronym SOLID, which you might have heard of in common literature, which stands for Single Responsibility Principle. So even though every microservice is a program, they do not need to be all of the same type of program, right? Some microservices might host web content, such as a self-hosted OIMP pipeline, or the .NET Core Kestrel server, and so on and so forth. Other microservices might be simple console applications, which might be similar to a scheduled task or a continuously running service. In fact, any executable program can run as a microservices if you think about it. So if you have like this ginormous web forms application, that by itself can be a microservice. But eventually the plan is to modernize, like they like to call it, your application, so that you break your application apart into single responsibility units or principles within the application. So you don't have to worry about taking down the entire application when you only want to operate a very small part of your app. And this is especially valid and very important when you have this large, ginormously complex applications which are very difficult to upgrade, to do continuous delivery upon, and so on and so forth. Basically, the entire conversation about microservices focuses a lot on the context of high availability, high resiliency, and disaster recovery, of course, but high availability mostly, right? You want to do an update, your application still has to be running, up and running. And just think about Netflix, right? You are not okay if Netflix goes down for whatever reason. You want to see that movie right now. You don't want to wait for it. Is Netflix down? Then you have a problem. You start tweeting. You start asking for support tickets, and so on and so forth. It used to be the story used to be different like 10, even 5 years ago. When you would see a service down, especially a web service, you'd be, okay, sure, no problem. I just go to sleep. Maybe the service will be up and running the next day. It no longer is like that. And you, as software developers, as software architects, have to have the responsibility of making sure that your applications are up and running and on a 24/7 manner. Now, traditional monolithic applications or application servers were different. Why and how? Well, let's explain that. Let's look at this example of a legacy application server. This server is hosting a complex application that is made up of multiple parts. In this particular example, there is a web server, some scheduled jobs or tasks, a data feed service like an extract, transform, and load job, a message queue, an API server. Like most systems built over the last several years, this application was created with the mindset that you will run on a server, a particular one, which you knew beforehand. Like, I'll even go further than that, and I will argue that 20 years ago, you even knew the exact model of the server, IBM or HP, X, whatever, 3650, blah, 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 and stuff like that. It no longer is like that, right? Back in those days, in the traditional monolithic application server, the relative memory and the CPU of the servers, they were considered early on. And the application developers, they created the system on that VM or on that physical machine. Each of these component parts was configured, or still is configured if you do it like that, and installed on the server directly. So that everybody works together on that one piece of machine, on one piece of hardware, or even a VM. The problem, though, is that as IT pros, and those of you who are IT pros, they can confirm that, back in those days, you treated your servers like pets, right? If your pet was ill, if it wasn't feeling good, the application wasn't really running as expected, the business might go down. Well, you know what? You should treat them like packs rather than pets. Here's how a monolithic application scaling used to look like. So when you wanted to scale, you obviously had a load balancer, like everybody else, but you were basically scaling the entire server. Of course, there's the entire theory of scaling up and scaling out, horizontally or vertically, in other words. Now, here's the fact. When you were creating a new scale, a new instance for your app, there was no way to scale an individual component within the application, which basically meant that if you had like a crazy number of static pages within your web app, you were scaling those web pages themselves as well. Even though you might use the CDN and caching mechanisms in front of the actual web application, you still copied over all the static content again and again and again, because you were scaling the entire app. And that's why it is so important to talk about microservices and breaking the monolithic application apart into multiple micro, like the name says, services, right? So microservices, on the other hand, are not developed in that way. Instead of envisioning a VM and then building application on it, microservices are developed as independent programs that will ultimately run in a cluster of virtual machines arbitrarily, right? So the application is composed of the same component parts just as before, but it no longer matters where those component parts are running. The service fabric system will organize them into arbitrary hardware based on how much capacity that hardware has, and guaranteeing that the services are distributed in such a way to actually resist failure. Now, it doesn't really matter if any of those servers has a copy of all of the parts together, such as the case of the monolithic application had in the last two slides. The cluster of servers as a whole will host the component parts for the application. Going even further, Service Fabric is one of Microsoft's services, which I would normally call an Azure service, but rest assured, it does not have to run on Azure. So this is actually an interesting conversation here. And itself is, in fact, made up of microservices that run on the same cluster as your application code. And this is an interesting concept to grasp. The full cluster is created in the Azure portal, yields these 6 services automatically, and each of them serves a separate and unique function, which you can largely infer by the names. So there are like a service is called Cluster Manager Service, which also hosts the Service Fabric Management Dashboard. Then you have the Failover Manager Service, the Fault Analysis Service, the Image Store Service, which holds the typed and versioned application packages, the Naming Services, which controls and addresses which microservices instances, each of them, and the Upgrade Service, which handles services version upgrades. This is actually the way the dashboard looks like when you look at within the Service Explorer, and hopefully through one of our demos, I will drill into the Explorer and the dashboard, and I will explain all of those components. You obviously see that there are like a number of links, especially the links across the top side are the navigation points, which will take you to the rest of the Fabric Management services. So there's a cluster map, there are a number of details for each and every single node and application and so on and so forth. There are metrics, there's the manifest, which is an XML file you can edit yourself, and a lot of different things. The dashboard itself gives you easy access to viewing the system health, to activate, restart, or deactivate Fabric nodes, to view application versions and images, packages, view application and service manifests, view metrics and application upgrades, simulate node failures and recovery, and a lot of many more things. Now, with the dashboard, you can monitor node states and see any errors, such as services failing below the required quorum of replicas. In the right side image, you can see some errors warning on the cluster, which are indicating that some services have fallen below their required quorum count, right? Which basically means that when you develop your application, you can specify, hey, I need this particular service, which is part of my application, to run on this minimum amount of nodes. Because otherwise, I'm not really offering or up to my SLAs as I suggested my customers I will. Now, let's talk about the clustering services and Service Fabric clusters as a whole. Service Fabric clusters, when created in the Microsoft Azure cloud, are made up of several different high-level Azure resources. The virtual machines that host the microservices are created as Azure Virtual Machine Scale Sets, which is a new service, right? Part of the entire platform as a service approach rather than IaaS, even though some do argue that it does involve more management than it should and so on and so forth. That's a different conversation. It does provide infrastructure, a scalable infrastructure, basically a VMSS provides a scalable infrastructure for the system of identically configured VMs. So you only have to take responsibility of making sure that you have all your applications and configurations done once, and the system itself will scale those across and span that number of code, binaries, configurations, and so on and so forth across all the VMs instances inside the VM skill set. Now, those virtual machines are connected to an Azure Virtual Network, and an Azure Virtual Network load balancer can distribute network traffic across the nodes, such as they were hosting a when you were hosting a website in the cluster. Now, one thing to remember, and this is very important, I actually started the presentation earlier on, and I already mentioned this. Service Fabric is polynymous, and this is a fun word, but here's what happens. As a technology platform, it is not limited to Microsoft Azure or even to a single cloud. It is fully polynymous, or in other words, multi-cloud. It is such a system that it can run on Microsoft Azure, it can run on Amazon Web Services, on whatever you want, actually, any other cloud hosting provider. Even in your on-premises environment, it still runs over there, right? You will have a better experience, though, when you are using Microsoft Azure, though, because the platform and its wizards and tools and so on and so forth are basically simplifying their configuration and deployments as well as official support. But you can certainly manually install and configure Azure Service Fabric platform onto other cloud virtual machines or other cloud hosting providers through their own virtual machine hosting options. So that's still valid, that's still an option. Now, the Service Fabric platform is also a cross-platform technology that runs across Windows Server and the Linux operating system. The Linux version is focused primarily on Java and .NET Core, but they both share the same microservices model and management interface. At this time right now, the Linux support is still under preview, so do expect some new features and tooling to be available in the future. Service Fabric clusters are made up of virtual machine nodes. Each and every single cluster is made up of at least one node type. A node type is a specific hardware loadout. In the Microsoft Azure Cloud, this will be a specific virtual machine size, such as D2 or F3 or whatever you want, or some other size that you may select. In other environments, it will be some specific set of hardware, which will include a certain amount of speed of CPU, memory, storage, and related specifications. Every cloud, though, starts with the primary node type, and you can then add additional node types for different virtual machine sizes. If you have more than one node type in your cluster, then you can deploy different applications and services onto the node types most appropriately to the resources needs. The end result is that you can most efficiently use the hardware that you are paying for. In this diagram here, you can imagine and you can see how multiple node types might look in a cluster. If you have two different node types, one large, one small, you would end up with a cluster that contained a set of large virtual machines and a set of small virtual machines. They are all part of one cluster, right? But now there are two hardware choices where you are deploying your application and services. As an example, you might have a web front end or API that you want to host on smaller virtual machines and some middle tier services that you want to host on larger, more powerful virtual machines. By placing them on different node types within the same cluster, you can achieve this configuration. Notice that the different node types end up becoming separate virtual machine skill sets in the cluster. Here we have one skill set of D2 virtual machines for the web front and another skill set of D4 virtual machines to host the more compute-intensive middle-tier services. Since the two node types are made of separate virtual machine skill sets, they can also be scaled separately. So for example, the D2 node type could be running up to 5 nodes, and the D4 node type could be running 7 nodes. And just to give you even more into the more in-depth information about how this works and how the entire nodes will be scaled across, since the Service Fabric cluster utilizes virtual machine skill sets to host their virtual machine nodes, they also get a feature from Azure called availability sets. This basically guarantees that the various nodes in the scale set will be placed across separate physical hardware units to protect against things like infrastructure failures, power supplies failures, network requirement, disk drive, or any other physical failures for that matter, right? If you've been around for the days of cloud services back in Azure, you might have eventually in IaaS heard of availability sets, but back in those days, there was within the cloud service the concept of upgrade domains and full domains. Those are still valid and still around for Service Fabric, and I'll explain those concepts again for those of you who are new to Azure. Now, since the Fabric cluster utilizes virtual machine skill sets to host their virtual machine nodes, they also get a feature of Microsoft. Oh, I already mentioned that, right? Oops, sorry for that. Yeah, my bad on the slide deck here. So availability sets will spread the virtual machine nodes across at least 3 different hardware units, which are also known as full domains, like I said earlier. This basically means that a complete hardware failure would only ever affect up to 1/3 of the running nodes, thereby protecting as much as possible of the running instances before new nodes can be provisioned or will be provisioned. Another feature of availability sets is the concept of update domains. An update domain, in comparison to a full domain, is an indication to the Azure Cloud Platform about how to handle infrastructure updates or even your own application updates. Basically, the Azure Platform will apply updates to one update domain at a time to guarantee that your application remains up during the process instead of bringing it down. Within a single availability set, you will get by default up to 5 update domains, but you can increase this up to 20. The more update domains you have, the longer updates will take, and this is actually a no-brainer. So when you update your application, you will not update it each and every single time for each and every single node or VM and so on and so forth. You'll only do a single process. But it is, in other words, Azure's responsibility to take your application package and have it updated on each and every single node, one at a time or multiple at a time, so that nodes, when they're part of the upgrade domains, they'll only specify, hey, I'm part of this whatever update domain. Let's update right now alongside with any other nodes which are part of the same update domain. This ensures that you'll always have high availability even during the update process. And this is one thing which is usually very difficult to achieve, especially in the IaaS world, because you have to take care of those processes by yourself. So when you do your updates, when something fails, the full domain itself will make sure that the system is up and running, and each and every single VM will be part of the full domain. When you do your updates, each and every single VM will be also part of an update domain. And the update domain, again, is an indication to exactly when a VM should be updated to the latest bits of your application, or still should be running the older version so that it is separated during the process. In conjunction with the update domain as part of the availability set, you can select the durability tier for your Service Fabric cluster node types. And you'll actually do this when you will create your first Service Fabric cluster inside Azure. The current available settings are bronze and gold, but silver will be available soon. If you select gold durability level, you'll have to choose a very high-end virtual machine size, such as D15 or G5, G standing for Gazilla. If you don't know what a Gazilla VM is, I really urge you to search on your favorite search engine for Azure virtual machine sizes and see what crazy amounts of specs you'll get from the Gazilla VMs. The silver durability level will later be available for all standard virtual machine size with at least one full core. The bronze durability level is available for all sizes right now. The settings is basically a way for you to obtain the privilege within the Microsoft Azure Cloud Platform for infrastructure updates to automatically be delayed for a certain amount of time. And this basically guarantees that your cluster maintains the proper quorum of the Service Fabric system services, and you have own applications and microservices during the Azure infrastructure jobs or updates. Since Azure infrastructure jobs or updates will effectively bring virtual machines down in each update domain, this is a way of protecting the services in your cluster from failing below the quorum settings. We'll talk more about quorum and replicas later. The reliability tier is another node type setting which determines how many replicas of the system services will be maintained across your primary node type. And since replicas have to be spread across node types in order to maintain reliability, this will also determine the minimum node count that you are allowed to allocate for node type. For example, if you select the silver reliability tier, and you will have to provision at least 5 nodes in the node type to guarantee that at least 5 replicas can run across 5 different nodes. You can always add nodes beyond the minimum, but you cannot have the lower than the minimum to still be eligible for the reliability tier. In effect, the more replicas you have for a given service, whether it is your own service or a system service, the less likely it becomes for any failures or updates to impact that service's uptime. This right here is a cluster map. Their cluster maps are Service Fabric clusters with their update domain and full domains on the graph. The map on the left side shows 5 nodes with 5 full domains, which basically means that each node is on its own full domain. The map on the right, however, shows 7 nodes with 5 full domains, and there is some overlap between full domains and nodes. Remember that you will always have at least 3 full domains in the availability set, but Service Fabric cluster often has as many as 5. This is how the node types, durability tier, and reliability tier appear in the Azure portal. So, building on top of the reliability tier and durability features of the underlying platform, the Service Fabric technology is able to offer self-healing services. Every microservices has a primary or active replica, and then some more configurable number of secondary replicas that are normally dormant. In this diagram right here, the light green microservices hexagon with the capital letter P is a primary node, and the 2 node services with capital S represent its secondary or other nodes, on other nodes. What happens right now is that the primary will go down. If the virtual machine hosting the primary replica will fail and go offline, maybe because of an infrastructure job or maybe because of hardware failure, one of those secondary replicas would immediately be prompted into the primary role and would become active and be able to receive requests from the network. The replicas that were lost due to the virtual machine failure will then be recreated on other virtual machine nodes in the same node type. The fabric will make sure that the replicas are always placed on different nodes so that one failure will never destroy more than one replica of the same service. You can see here how the two top nodes now have an extra service since one node was lost from the cluster. And very important to say is that you will never, supposedly, you should never end up having the same microservice on the same node multiple times, right? You'll always have the same application into the minimum amount of nodes you have configured, right? So if you have like a stateful service, that will by default be at least 2 secondaries, at least 2 replicas, and 1 primary, and they will always be spread across the entire cluster. A new virtual machine node will be provisioned according to the node type and joined to the cluster to replace the node that was lost. Once the VM node is ready, obviously that doesn't have any running services on it, so once the node replacement is connected to the cluster and ready, the fabric will take and then rebalance the services across all the available nodes for an even distribution. And at this point, the fabric has completely healed from the failure, but throughout the process, the system has never down thanks to the replicas and the full domains. And I know it has taken me like a very long amount of time to explain all this process. This actually happens within seconds. Most of the times, as a user, you don't even realize that you're running on a different node, right? This is the power Service Fabric brings to you. Upgrades to the microservices work with respect to the update domains that have been configured for the node type. The fabric will update one domain at a time and do the process, and it will not proceed to the next update domain within the process until the previous update domain is finished updating and reporting healthy status. The fabric will also automatically roll back failed updates. Through this pattern, the Service Fabric is able to offer zero downtime updates, and there are even ways to customize how the fabric handles this process, such as how long it waits for updates to complete, and how it can determine the service's overall health, and so on and so forth. If you want to increase the scale of your service, now you can do it simply by adding additional nodes to one of the node types within the cluster, just like that. So for example, you might increase the node count from 6 to 8, like in this diagram, and this will provision 2 new VMs according to the node type, and then add them to the cluster. Once those node types are ready, the Fabric service will then rebalance the application services across all of the available hardware, which will result in more available hardware resources per server instance. Since Service Fabric Cluster is built upon virtual machine scale sets, you can also configure auto-scale rules. These rules can be configured based on either on schedules that you set or on the virtual machine metrics such as average CPU utilization and so on and so forth. By enabling auto-scale for the virtual machine scale set, you can have the cluster grow to handle increased demand automatically and then shrink back down to its minimum size once demand decreases to save basically resources. This is exactly how it works. So you can scale up, and then when there is no longer a demand, you can scale down. But do rest assured, don't always scale down to the minimum which no longer offers SLA. So do choose your numbers wisely. The Service Fabric platform offers security for your nodes in a few different ways. Primarily, security is handled through the use of X509 certificates that are installed into the nodes by the Service Fabric platform when they are provisioned. Those certificates are then used as node-to-node security by the nodes to authenticate with one another before they will communicate. Any attempt by a node to join the cluster without a certificate will be completely rejected. Any other use or another use of the certificate is client-to-node security, whereby a system client, such as your web browser or Visual Studio, must have the private certificate in order to communicate with the cluster manager service or the web dashboard. Again, any attempt to communicate without a certificate will be completely rejected. There are also additional advanced ways for you to use your own certificate at the application level. In addition to the certificate security in the cluster, you can also configure Azure Active Directory for role-based access control, or RBAC, to configure who in the directory should be able to access the management portal for the cluster. On top of this, of course, is the Azure Load Balancer,
and the network security group, which will control network traffic in and out of the virtual machine network and the virtual network, sorry, to which your cluster is attached. Let's talk about application packages and how you should think about Service Fabric in the context of a software developer. Each application that you will end up deploying into Service Fabric is made up of maybe an application package. And I'll be honest, as a developer, when I first was presented to Service Fabric, I originally, when they were emphasizing on microservices and entire conversation about splitting your monolithic application across multiple microservices, choosing a microservice was difficult, right? But most importantly for me was, how do I, as a software developer, end up architecting my projects, my solution within Visual Studio, if I'm a .NET developer, C#, whatever have you, right? I was used to developing the application and the entire system, the infrastructure in one way. Do I right now have to create multiple Visual Studio solutions? What about a single application? Do I have to deploy the services one by one as an instance because this is a microservices platform? So do I have to work with microservices? Well, the answer is no, actually. The deployment process goes way easier, and the application type sits on top of everything else. So each application that you will deploy within a Service Fabric is made up of an application package. This package is organized like a tree with the application itself on top and each of the microservices within it at the bottom. There are certain details and settings configured at the application level, and there are other details and settings configured at the service level. Now, note that there are the use of the word service here, and I'm talking about microservices. But whenever you see service, that's the same thing, right? As you can see in the diagram right now, each of the microservices inside of the application will have its own package that consists of code, configuration, and sometimes also data files. Also, not only the application itself, but each of the services within it, and even the application components within each of those services are given version numbers, which are also used during the service updates. You are allowed to deploy multiple applications on the same node types in the same cluster. You do not have to limit your system, in other words, to one application per node type. This basically, in common literature, is called high density, because back in the days of cloud services, the main problem was that when you were designing your application and starting a new Visual Studio solution with projects for your cloud service infrastructure, we're basically creating a server role. Now, those server roles are actually whatever you see in the service type. So the service type is an analogy, more or less, to the cloud services roles, right? The problem back then was that when you were creating a new server role, you were basically creating a project, whether that was a web API, an MVC app, whatever have you. And when you were deploying your cloud service, each one project ended up being at least one instance of a VM, but in order to achieve SLA, it had to be at least two. And if you wanted to have awesome updates and awesome full domains and so on and so forth, you even had multiple instances. The problem was that for whatever small application you wrote, whether that was a console app or whatever have you, you were spinning up another VM, right? What we want to achieve with microservices, besides splitting the monolithic application apart, is also high density. One node still might have additional resources available, so I want to have multiple application services running on the same node alongside with others. At the application level, the top of the diagram we saw previously was the application package. This package is a deployment artifact, like the cloud services, back in the cloud services role, the CSPKG file, right? Now, this application package is a deployment artifact, like I said, onto the Service Fabric cluster, and is also mirrored in your project if you are using one of the Visual Studio templates. This application package basically contains a manifest file called the application manifest.xml that holds application-wide settings. These settings include the application version number, the description of the application, and the microservices to import along with their individual packages. There is also a parameters file that is paired with the application manifest that you can override defaults or settings or configurations in the manifest, usually on a per environment basis. When you create a service fabric application in Visual Studio, you automatically get parameters for the cloud, for a local 1-node cluster, and also for a local 5-node cluster. Each of them has environment-specific settings, normally around instances and partition counts and so on and so forth. Each microservice will have its own manifest file with service-specific settings. These include the type name, the executable programs to run when the microservices is started, the configuration files, and any network endpoints that service requires, AT, 443, whatever other endpoints you want to have for yourself and for your application. Microservices also contain their own deployment packages that fit within the greater application package. In these service packages, you will find the code, the configuration files, and any other optional data files. The code portion of the package is made up of the executable program and any related libraries or scripts it might need to execute. This can include DLLs, jar files, batch files, and so on and so forth. The configuration portion of the package is made up of settings.xml files, which can contain and will contain some settings around replicas and any other advanced settings. The data portion of the package will contain any other data files that the service might need. So for example, if the service is a web server, the data package would have the HTML, JavaScript, CSS, and any other images or any other plugins you might be using inside your web app. Now, last part of the conversation will be about and around services. So let's see what the services are and how to think about them. There are multiple service fabric service types. There is the actors model, which is so popular. Then there is the stateless services, websites, self-hosted APIs, whatever you want. Stateful services, guest executables. Guest executable is quite an interesting fact, because what happens here is that you take a running application which you have developed, which has no idea that it runs inside the service fabric, has no idea and will not be touched for running on the service fabric, will have no context towards service fabric by itself, and will still run as a microservice within the cluster, right? And this is actually an interesting concept, because if you have to deal with full domains, update domains, you have to offer high availability towards your customer, rather than doing all the infrastructure craziness underneath your applications, you can just take your app and run it as a microservice. Obviously, you will not get the full advantage and the power Service Fabric has to offer, and the microservices pattern and software development pattern that is has to offer, but you still get so much more benefit. And actually, many people usually ask me, okay, but what about pricing when it comes to Service Fabric? Well, you know what? You're actually, at least in Microsoft Azure, you're actually only paying for the actual VMs, the compute and storage and so on and so forth. You're not paying anything extra to have Service Fabric running, which basically means that you can get the full benefits of Service Fabric and the entire orchestration things it does, and only pay for the VM, which you already did, right? So it makes a lot of sense for those scenarios as well. And in my personal opinion, cherry on top is containers. So within a microservice, the service itself can be one of your containers. And this has a lot to do and is super nice and interesting when you think about the Docker images files and have those images, Docker images, run as a microservices, because eventually that's only an application itself with its binaries and operating system libraries and so on and so forth, which are dependent on it. But there's absolutely no time to cover all of those. And there is a particular training which will cover those in more depth. Just to quickly go through the entire conversation here, stateless services are basically services in the Service Fabric ecosystem which are stateless, right? Cloud applications nowadays have learned us to develop these stateless applications. Basically, stateless applications and services, by definition, they do not have any managed or inherent state, so there is effectively no consequences to the number of instances that exist. There is nothing that one instance knows that the other instances need to know in order for the entire application to work. This is the normal state service type for web servers and API services and servers or any other service where state management is simply not necessary. Because of this, it is common to see stateless services configured to have one instance per role, which is represented by a -1 in the application manifest file. With this setting, the number of nodes equates to the number of instances that the stateless of the stateless service. So, like in this diagram right here, 5 nodes equals 5 instances of these two services, 1 per node. This is a very useful pattern for web service and API servers specifically because it makes addresses and load balancing very straightforward. If you know that every node has an instance of a service, you can load balance traffic across all of the nodes, round robin. That's like snipping your fingers and that's it, arbitrarily, right? And know that it will work no matter which node you are talking to. It is also possible to configure stateless services with a fixed instance count if you have to control the number of instances manually instead of 1 per node. If you want to increase the scale of the stateless service, you simply need to add additional nodes to the cluster. In this picture right here, we have added one additional node, the one called node 6. Once the node has been provisioned according to the node type and joined to the cluster, the service fabric will deploy new copies of the stateless service onto it. One more node means one more copy of each of the stateless services. Stateless services are commonly created as websites, web APIs, and web services. They are also a direct upgrade path from the cloud services I've mentioned so many times before, since they are stateless by definition. Now, stateless service communication, basically, when we talk about communication within the services we're deploying across the entire cluster, you have to remember that each service has a unique URL with one or many ports. Service Fabric itself, as a service, can share the ports on the same node, so multiple services can use the same port as long as you have unique URLs, which is also super important if you think about it, because you no longer have to worry about hosting multiple web apps, which all have to listen on port 80. It's the Fabric system, it's the Fabric responsibility to listen and to correctly route the request towards the correct application, and obviously within the node. Stateful services, on the other hand, are scaled very differently. Instead of instance counts, like stateless services, stateful services achieve availability and scale through the use of partitions, which are often represented as GUIDs, or as long as a long integer, but can be customized as strings as well. But that's a different conversation. Each partition is a stateful service. In a stateful service, equals to a unique instance of that stateful service. So for example, if you deploy one stateful service, which was configured to use 25 partitions, for example, onto a node type with 5 nodes, it would create 25 instances of the service, and each node of the service fabric would have about 5 of those instances. By adding additional hardware nodes, the partitions can be rebalanced on the cluster, which basically means that the number of partitions ends up being the maximum potential scale of the system. If you have 25 partitions, those 25 partitions can only ever take advantage of a maximum of 25 nodes. By adding a 26th node would not increase the scale because the number of partitions is fixed and does not grow automatically. Not only this, but you're also not allowed to change the number of partitions for stateful services as part of a service update because it is set at the time of the service when the service is first created. Because of this, you should think through how many partitions you need before you deploy the service to a cluster. As part of the decision, you should think about the maximum cluster size for your application and also how you want to access the state of those partitions. Now, rest assured, there are workarounds if you do have to change your partitions during runtime, and those workarounds actually mean spinning up a new cluster because, again, those numbers are defined and specified when you first create, when the service is first created. You can also recreate everything from scratch, so that's obviously another option. But as a best practice here and as an advice, think through how many partitions you need before you deploy the service to the cluster. So here's how our nodes will go. Rebalance everything. Awesome. Each partition of a stateful service has access to its own private, durable, and replicated state. That way, the stateful services access the state is through the state manager, and I will show you that in a few minutes in my demo. That particular object is supplied by the platform. So the state manager object will provide access to state-specific types across state stores, also known as reliable collections. These two collections types are reliable dictionary and reliable queues. Both of these collections are generic and strong typing. The state is stored for the Fabric platform on virtual machine nodes that are hosting the partitions and replicated onto their secondary replicas automatically. Even if a primary replica were to completely fail, any secondary replica can immediately pick up where it left the exact same state. Now you may ask yourself, why do we even have stateful services in the first place? Weren't we all taught that we have to keep everything stateless in the cloud? Well, yes, that's true. But then again, at some point, if you think about it, the persistency layers of your application end up being a completely different service. Most of the time, SQL Server, NoSQL storages, whatever approach you wanted to take, whatever the case, doesn't really matter for this conversation, which were additional network service calls. And those service calls were HTTP, TCP, whatever had you, they all automatically also mean network hops, which means decreased performance and increased latency because of network hops, right? So here's a thought, and here's the full reason for why we have stateful services as well. Sometimes when you were developing applications, you had your web front end as a first tier, as a first flag, then you had a call from your front end tier towards your back ends, and from the backends, back in the day, you had another call towards the persistency layer, Azure SQL Database, SQL Server, Azure Storage, whatever had you. Now, in order to increase performance, what usually probably did was to implement the caching layer between your APIs and your persistency layers. Now, that's good. I'm not saying that that's bad, but here's the thought. For some services, because again, remember, the entire concept is to have polyglot persistence, polynimbus if you want to have the same application running on multiple clouds, poly whatever have you, which basically means you don't have to store everything inside the same persistency layer. There will be some services, which in other words means some part of your entire big application, which can have state stored alongside with the data running. And this is why you have stateful services. Rather than doing additional network hops, you take the entire information, which is stateful, running alongside with the code, and important, is also part of the transaction, which is what I'm saying when I say that the secondary replicas can take over. Basically, they will have the exact same copy running on their nodes if my primary node fails, like you saw in the diagrams earlier. The reliable dictionary is one of the functions. The reliable queue was the other. Functions much more like the normal C# collection in terms of adding and removing values. But because it is replicated across nodes and durable, you normally need to wrap any code that uses it within a transaction, like he said. So within that transaction, you can perform normal dictionary tasks with one caveat. The reliable dictionary type, which is an interface, so it's iReliable dictionary, does not implement the enumerable interface. So you cannot loop over it with normal loops. Instead of iEnumerable, the reliable dictionary implements async enumerable, which does give you access to an enumerator,
but you have to work with the async and await pattern yourself, especially if you're C# developer. This probably makes a lot of sense. Now, here's the code. You can see how to enumerate the iReliable dictionary. The actual code here is reading all the values from the iReliable dictionary and returning it as part of the API action method, which is why you see a view model object. On the first line, you can see how to retrieve the iReliable dictionary from the state manager right here. So here it is. After that, a view model object is created from an API action result, and the state manager is used to create a transaction. The transaction is there because without the transaction, you couldn't make sure that you're getting the actual data. It still has to be atomic, right? You will have replicas across multiple nodes. You still have to make sure that if your primary node fails, you will not have inconsistent dates or ghost data or anything like that. So once inside the transaction, the enumerator is created from the dictionary, and the enumerator move next async, this call over here, is used with the while loop to iterate the content. So take note of this pattern because it is quite different than using a normal for loop or LINQ expression. And for this reason, it turns out, is because all of these methods need to access the dictionary, and they are all asynchronous and require a wait, right? Now, this itself will run synchronously and will wait for a task, but underneath everything, it does take advantage of the async await pattern. The reliable queue, on the other hand, is a message queue. And as you would expect, it's very similar to the reliable dictionary, and you only need to wrap any access to it with a transaction, and you're good to go. Now, as this obviously, as long as you have the async await pattern implemented. This queue exists with a single partition and within a single partition, and it is not a queue across multiple partitions, though. Now, something else to consider, and closely ending the presentation right here because of the timing reasons, when you are using the reliable connection for stateful services, is the impact of changes to the objects that you're storing inside those collections, right? If you make changes to one type that you're storing in a reliable dictionary, and this change causes the new code to fail when reading all the objects, for example, or vice versa, it causes old code to fail when reading new objects, your service update could fail and be rolled back. This can happen because the update domains will be updating replicas at the different times, since they will exist on different nodes. When one replica is updated, the other replicas will be using the same state, so you have to account for both possibilities of update services reading old state and older services reading new state. The recommended way to handle this is through the use of data contracts, similar to what is done in WCF, Windows Communication Foundation Services. These data contracts are normally expressed as attributes on your data models. There's a URL on the lower section of this slide. You should see that particular URL for more detail on how to implement the version data contracts for your stateful services. As a final note, remember that the state stored in these collections is only replicated between a microservice partition and its replicas. It is not replicated across clusters or any other partitions. If you want a microservice in one partition to communicate with a microservice in another partition, you are going to have to write that code yourself. And with that being said, let me quickly go back to the questions pan. If you do have any questions, I'll be happy to take them. If not, I'll have to thank you. It was a pleasure to present this content. Make sure that there is so much more to talk about, and the opportunity is there to offer this. Ashley, would you take over?
Yes. Thank you, Alex, and thank you everyone for attending our webinar. We are offering a 30-day free trial to customers for our new, for our online training service. For individuals, just input discount, try Opsgility, all caps, when creating the subscription at opsgility.com. Also, if you are interested in a business pilot, we do have that for a 30-day free trial. Oh, goodness. Sorry about that. Again, if you are interested in the 30-day free business pilot, email info@opsgility.com. These are a few classes that we have to offer. And if you would like more information, you can also email at info@opsgility.com. And thank you for attending. And Alex will be hanging out for a little bit to answer any questions. Thank you.